introduction behind what happening in Southeast Asia liner grade. Okay, and then goes to how this chemistry is working, and then I show you some specific lab tests for this chemistry, and then the real case study. So it's actually still related to the topic in the earlier discussed today. Basically, the challenge that we face in Southeast Asia is quite similar with in India and globally, I assume. This fiber savings, of course, the competitiveness in the industry, especially the coming supply this liner grade from big capacity machine in China that goes in Southeast Asia, demanding the producer in the local Southeast Asia need to be more cost effective and efficient. They try to optimize their main raw material, which is the fibers. So either by substituting with the so-called low cost material, or try to get an enhancement in the final liner quality, so they can more competitive in the market. And quality upgrade, we see more and more in Southeast Asia, especially high demand for, they call it H grade liner board, which is requiring a quite high burst index. We call it in India as burst factor, which is basically similar, just different unit. And then we know that many and many more new modern machine, which is a very high capacity from 1,000 ton per day up to 2,000 ton per day capacity, and machine can be run from 700 to 1,500 meter per minute. And that one will be facing different challenges, like the productivity and runnability of the machine, because basically even modern machine, they're still using a recycled OCC, which is the strength and the quality is degrading over the time. And yet the other thing is energy saving. Many mills in Southeast Asia have different strategy in how they get this energy saving. Some customer in our mill in Southeast Asia already try, by saving the energy, they're opening this ice press, so they can run faster and they less energy to produce paper. But this strategy actually causing a more challenging demands, such as the strength, especially if they are producing this fluting, and mostly the strength gaining from the size press. So without the size press, they need really very strong chemistry or really process to gaining or at least maintaining the same quality of paper. Okay. And chemical savings, with this for challenging, actually the demand of chemical is more and more. But on the other hand, they need also to do some cost saving any aspect including the chemicals. So this challenge for this liner grade in Southeast Asia, that causing them to use quite a lot of strength chemistry to get strength property of the product with the liner. Basically, this topic is liner as well as the medium grade. So talking about the strength, actually I'm not talking about just the chemical. Basically, it's synergy of these three components. And of course, the main driver will be the fiber material. But this is actually also facing limitation, either the availability or the cost as well. And we know this. The other factor is the parameter of the process. This can be also positive and can be also the negative factor also to impacting the final strength product. And also the chemical. Chemical, if we talking is overall, some chemistry have interaction between the chemistry. So the choice of the chemicals is important to enhance for its purpose than this topic. Okay, in general, when we're talking about strength chemical, either natural product or synthetic product, basically it works by enhancing the fiber and fiber bonding in terms of quantitative and qualitative. Okay. Yes, just talking about when the strength can be improved either by those three factors, then normally the paper making can have a choice, either trade off those benefit to something cost saving, like they can produce a lower GSM, or choosing to find the lower cost fiber material, or in mechanically maybe can reduce the refining energy, something like that. Okay, and then if they want to keep the strength, then they can enter different segments so that they can sell their product to the higher grade. Okay, and then talking about the dry strength choice, as I mentioned, actually the most common natural dry strength product if the paper making use would be the starch. But there is existing also synthetic dry strength, which is the most common one actually is the amphoteric pen. Okay, but in this topic, in Southeast Asia, like in the past previous 5-6 years, mostly they are using starch in combination with this amphoteric pump. But since then, they are more interesting to synergy this amphoteric pump with this calcium pump. So now after this slide, I will talk more about why G-pump is benefit to use together with this amphoteric pump. Before that one is G-pump. What is G-pump? Actually, G-pump, the backbone is similar, is acrylamide. You polymerize that one and cationize that one with that one, and you get this cationized pump. Then you react it with Cleoxal and you make it Cleoxalate pump. Simple way is G-pump. How they make that one actually depend on the raw material and the process. We know the G-pump actually in the market have a very short life. The one that we know is sometimes below 30 days, the product already cannot be used. So it needs as fresh as possible. But in our company, actually we have a product and we know how to make the G-pump is more stable, because the stability also is affecting the final performance of the product. Specific product, this, it can have a long stability in the test up to 4 months, but in the reality, actually in the real machine case, it can be used, even be stored up to 6 months. Okay. And even in the tropical temperature, which is a Southeast Asia Pacific temperature, it's always like roughly about 35 across night and days. And why this G-pump? This G-pump actually is high cationic charge, higher charge cationic compared to the amphoteric dry strength. Okay, so in nature, it should be less sensitive to this high conductivity environment, and also less affected with the anionic trace, the one in the paper making that using a recycled OCC. Okay, and if you see the structure itself, this is another benefit of G-pump. G-pump, after become the final product, they have to secure a group, which is this part amino group. It will react with a cellulose side and creating a hydrogen bond. This one actually is similar with the normal amphoteric dry strength, which is also forming this hydrogen bond. But the benefit of that one, this G-pump have this aldehyde group, which is if react with this cellulose side, it will form a covalent bond, which is, we know covalent bond actually is stronger than this hydrogen bond. And the covalent bond that they made actually, depending on the pH, it can be hemiacetal or can be also this acetal bond. Okay. And okay, this is the benefit of this G-pump. As mentioned before, since this one is cationized or more cationic than the amphoteric dry strength, it gives benefit. We often see improving is this dewatering and retention, sort of acting like just normal flocculant that you use normally in the liner making. Okay, but I'm going to explain why it has a benefit of this wet strength and temporary wet strength. As previous slide I informed, there is an aldehyde group that can create a covalent bond. When covalent bond is formed in hemiacetal bond, actually this reaction is reversible and also starting to make strength, develop the strength along when the water is removed during the paper making. So we see many cases that this GPAM actually improve the runnability because sort of giving this web strength. While for temporary web strength, it means if GPAM, there is another case, used for tissue or towel, it gives improvement as a web strength, but it's not permanent. So when the tissue is broke again, it can be easily decay and then disperse in the paper when you recycle tissue or napkin using combination of GPAM and wet strength. Okay, now it's going to the laboratory test. So this graph actually is showing the testing between amphoteric dress strength and GPAM as a single component. As you can see here, for strength, then GPAM actually can replace one-on-one on wet basis. Okay, and this in this case we focus on this burst index. Okay. And in this lab test, we try to combine GPAM and amphoteric dress strength and fix at 20 kg per ton as a total wet. And then we try to combine, for example, in this graph, 75% of GPAM means 75% of this 20 kg, and the rest will be the amphoteric dress strength. And you can see here, in previous slide as a single, you get only this bursting index roughly about 2.8, but when you combine, you can get an enhancement in the strength. Okay. I mentioned that one. More often, we always see the effect to the dewatering. So by itself, GPAM have a very good dewatering comparing to amphoteric dress strength. So when you combine, then you can see the effect. Instead of you are using 100% of the DSR, normally either not affecting the dewatering or even negatively affecting the dewatering. Then with GPAM, you can get better benefit of the strength as well as the dewatering. Okay, it goes to the 3 case study. One case study actually in the small low GSM paper bag, and you can see here 30% OCC and 55% mixed waste, and 50% from their own probe. And in this case, actually, GPAM works like a dewatering aid. It can replace the silica with additional GPAM on one. So they are using already silica 1.2 kg per ton as wet, and we can remove that one with GPAM 1.2 kg per ton as wet as well. Okay, and you can get still maintaining roughly similar tensile and bursting index, maintaining dewatering, but better turbidity and lower consistency of wet water. Second case is a bit bigger machine, and this producing corrugating medium, and this is the furnace 70% recycle, 20% mixed waste, and 10% broke. And this is the wet end parameter, and this is basis weight they make in this machine. And in this case, actually, GPAM added on the top of amphoteric dress strength that they already use. So it can reduce the amphoteric dress strength from 17 to 15 kg per ton in the thick stock, and then amphoteric dress strength eliminate this one 4 kg in the thin stock by adding GPAM 6 kg per ton, while still maintaining this strength and improving the watering and also the machine productivity. Okay. And then the last case, actually, this is the big machine. They're producing so-called high grade, high strength liner machine, which normally they have a spec 3.8 burst index, or if you convert it to burst factor, it's roughly 10 by 10, about 38. And we normally this machine use up to 40 kg per ton of amphoteric dress strength, and then by adding the GPAM 7 kg per ton total, but it's 2-ply machine, and then we managed to reduce to 30 kg. So total dosage is reduced to 33 kg per ton, or 10% reduction. So in summary, this GPAM actually, the product that I present have long-term stability, and the performance is quite good, easy to apply, and when it's applied with amphoteric dress strength, it can give benefit to reduce the overall cost, improve strength, better productivity due to the better runnability, and also wet strength that sometimes developed by GPAM, and also somehow this is the load of that one. If you improving the retention, of course, the water consumption will be better in terms of your fiber recovery system. And Chipam is easy to use, pump and go chemical. Okay. Thank you.
Thank you.